Hi everybody, today we are finally going to learn how we use the antiderivatives that we've been practicing to find the exact areas. And again, when we're talking about exact areas, we're talking about the area between a curve and the x-axis, or really finding exact values of integrals. So far, we knew that we can find exact areas using geometry. Right? But we are pretty limited there because it only works for geometric graphs. Okay, we also learned that we can approximate areas using our rectangular approximation methods. Let's see, MRAM, and our trapezoidal rule. But again, that was just approximation. It didn't give us exact areas. So the big idea for today, and what's going to be super important for us the rest of this chapter and going forward this semester, is how can we find exact areas when we don't have nice, neat geometric graphs? And so that is where our fundamental theorem of calculus comes in. Obviously, by the name fundamental theorem, we could tell it's a pretty big deal. So here's what it says. It says if f, a function f, is continuous at every point on a given interval, and capital F here is the antiderivative of f, then the integral from a to b of f of x dx equals the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. So again, just to be really clear here, these capital F's are the antiderivative of our function f, and then my b is my upper bound of integration, and a is my lower bound. Right? Which is super powerful stuff because, what this is saying is that if I can find an antiderivative for f, then I can also find the exact value of that given integral. So that's what we're going to be practicing today, is using this rule to calculate the exact values of integrals. So again, obviously this is going to require you to really be good at calculating those antiderivatives, because without that we're pretty stuck at this point. So let's go ahead and look at this one. So for number one, it says use antiderivatives to evaluate the following integrals. So again, my idea here hinges on the fact that I can find the antiderivative of f. Right? In this case here, this is my function f of x. So I need to find the antiderivative of that. Well, luckily, this is just a nice polynomial function. So the antiderivative of 2x, I know, is x squared. Minus 2, the antiderivative of that is minus 2x. And then again, we always have our plus c. Now, we're going to use this notation here, and I'm going to put from 0 to 3. Right? That means I'm going to evaluate this integral from 0 to 3. So here's what it looks like. I first evaluate this function at my upper limit. So I'm going to evaluate this x squared minus 2x plus 3, or plus c, at value 3. So instead of x, I'm going to do 3 squared minus 2 times 3. Now c is just a constant, so it just stays constant. So that is the first part, right? All these 3's are coming from my upper limit of integration. Now, this said here to subtract. So I'm going to subtract my function evaluated at my lower bound. So I'm going to use parentheses here because I have a minus. Those parentheses are really important. So now I'm going to substitute 0. So minus 0 squared minus 2 times 0 plus c. And again, the 0 came from now we're evaluating at the lower bound. So you can see how this matches here. My antiderivative evaluated my upper bound minus, our minus is here, my antiderivative evaluated at the lower bound. And now we just need to simplify that stuff. So let's see what we've got. I have 3 squared is 9 minus 2 times 3 is 6. So 9 minus 6 is 3 plus c minus, let's see, I have 0 minus 2, so 0 minus 0. So all I have in here is a positive c. Now, my c's are going to cancel out. So all I'm left with is 3. So that tells me that the exact value of this integral is 3. Now we won't do this every time, but because this is a nice linear function, we can kind of relate it back to what we did with geometry. So I'm going to do a really quick sketch of my function here. Right, I know this is line. It has a y-intercept of -2 and a slope of +2. So when I'm at 0, I'm at -2, and then I go up 2 over 1 each time. And 3, let's see. So if I did this right, here's what my line looks like. And that's rough, I know, but it gives us the idea. So if I'm evaluating from 0 to 3, I have this portion which is below the x-axis. We know that's negative. And then I have the portion that's above the x-axis here, which is going to be positive. So I have a negative area here. I've got a triangle. It looks like the base is 1, so 1/2 times 1. The height of that triangle is 2. And then I'm going to add 1/2. The base of this triangle is 2, and the height is 4. And so I get a -1 plus 4, and that's equal to 3. So again, there's kind of the visual of how this works. We're finding the areas of these triangles. Again, that's the same value as that integral. Okay, so for the rest of these, we won't sketch any more graphs, but we're just going to be working with our fundamental theorem here to find these exact values. Now, one thing I do want to show you, obviously these will be no calculator problems. You'll need to show your work to find the values of these integrals, but I do want to show you how you can check this in your calculator. Say for some reason you didn't have the solutions, your calculator will do this for you. So if you go to Math, and then pick, if we scroll down, 9 is this fn int. It'll show you the integral notation. It's all nice. If you use your math print, hopefully you get this nice view. And I'm just going to plug in exactly what I have here. From 0 to 3, my function is 2x minus 2, and I type in dx, hit enter, and I get a value of 3. So it's a nice way to check that your work is correct. Again, most often you will not have your calculator, but when you're doing your practice, it's nice to be able to do a quick check. All right, so let's keep going here. So if I'm going to evaluate this, I need to know what my antiderivative is. Well, this one's nice because the antiderivative of e to the x is just e to the x. So my antiderivative is 2e to the x, and I'm evaluating from -2 to 0. So I'm going to start by evaluating at 0. So I have 2e to the 0 plus c. I'm still using my plus c's. And then I have to subtract 2e to the -2 plus c. So now I'm going to simplify. E to the 0 I know is 1, so I have 2 plus c. I need to distribute this negative because I have two terms inside those parentheses. So then I have minus 2e to the -2 minus c. So now my plus c and my minus c cancel out, and the value of my integral is 2 minus 2e to the -2. Now, you're noticing here, hopefully, those c's are always going to cancel out. If for some reason they don't, make sure that you're properly distributing that negative. That's probably going to be the only issue you might run against if you're noticing you're having problems with those c's not canceling out. All right, we'll do a few more. We're not going to do everything on this page, but we'll go through a few more to make sure you've got kind of a, hopefully, a fairly solid idea of how this works. And then we could talk about the rest in class. All right. So for number 3, I need to find the antiderivative of secant squared of x. That's a nice simple one. I know that is tangent of x. And I'm going to evaluate that, let's see, from pi over 6 to pi over 4. So what that tells me I need to do is I'm going to evaluate it at my upper bound, tangent of pi over 4 plus c. Actually, sorry, my c should have been up here in my antiderivative. Now I know that looks kind of messy, but I should have had the c here with my antiderivative. So I have tangent of pi over 4 plus c minus tangent of pi over 6 plus c. Now, tangent of pi over 4, I know tangent of pi over 4 is 1. So I have 1 plus c. I'm going to distribute that negative. Tangent of pi over 6, let's see, it's going to be 1 over root 3. And again, I'm distributing that negative, so I'm subtracting the c. My plus c and my minus c cancel, and I get an antiderivative, or a value of that integral, is 1 minus 1 over root 3. Now again, if I were feeling unsure of myself, this one might be a good one to check in my calculator. I do have to be a little careful because I have this secant squared. So let's see, 1 minus 1 divided by square root of 3, I think should be about 0.423. Let's do the integral. So math 9, I have from pi over 6, from pi over 4. Now secant is 1 over cosine. So I have 1 over cosine of x, and then I have to square that. Let's see. I'm going to insert my squared. Nope, that's not where I want it, is it? Yeah. And then I have dx. Okay, and I can check that I got the right answer. Okay. Let's see. We're just going to do one more. I'll leave, I think, these two. Let's look at this one here. My antiderivative now, remember, this is really 4 times 1 over x. And I know when I have that 1 over x, my function is the natural log of the absolute value of x. So my antiderivative is 4 times the natural log of the absolute value of x plus c. Being careful to remember that. And I'm evaluating from 1 to 4. So I'm going to start with 4. So I have 4 times the natural log of 4. That's positive, so I'm not so concerned about that absolute value. I have plus c, and then I'm going to subtract the lower bound. So 4 times the natural log of the absolute value of 1 plus c. Almost forgot my parentheses there. So I can't do much with this one here. I have 4 times the natural log of 4 plus c minus, well, the natural log of 1 is just 0. So I have 4 times 0, which is just 0. And then if I distribute my negative, I'm just subtracting c. So I get an answer of 4 times the natural log of 4. Okay. All right, we'll stop there. When we start class tomorrow, we'll kind of go over these remaining examples together before you launch into the practice for the rest of the period. All right, see you tomorrow.